Hi students, welcome back. Let us continue with the various methods of handling the deadlocks. So in the previous videos I explained about deadlock ignorance and deadlock prevention. Now let us see the deadlock avoidance. So to avoid the deadlock, the main important thing is you have to do the simplest and most useful model requires that each process declare a maximum number of resources that it may need. Means before the starting only we have to declare each process, whatever the process we are taking, P1, P2, P3, so those process has to declare maximum number of resources that it may need. Means how many resources this process 1 needs. Suppose it needs 4, process 2 needs 10, and process 3 needs 20, like that. So first we have to declare the maximum number of resources that each process need. So if you do like that, you can somewhat avoid the deadlock. And deadlock avoidance algorithm dynamically examines the resource allocation can never be circular weight condition. So we are using some deadlock avoidance algorithm. This deadlock avoidance algorithm helpful to examine the resource allocation, means to which process we have to allocate the resources, so that it cannot form the circular weight condition, means it cannot form the loop. So to take care about that, this deadlock avoidance algorithm will be used. So by using this, by keeping these 2 points in mind, so we can avoid the deadlock. The basic facts that involved in deadlock avoidance is, if a system is in safe state, there should be no deadlock. So what do you mean by the safe state? A safe state means if one process is allocated to one resources in some sequence manner, okay, means without any confusion and without any conflicts, then your system is in safe state. Means your process has to be execute successfully without any problem. So then you can say your system is in safe state. So when your system is in suppose your system is in safe state, means obviously there should be no deadlock. Suppose if a system is in unsafe state, means some problem may occur, means some deadlock may occur. There is a possibility of deadlock. I can't ensure that the compulsory the deadlock is there if your system is unsafe. There is a possibility of deadlock because the deadlock will occur rarely, not frequently. Whenever, means if you want to call your friend, again your friend is calling to you daily, it won't happen at the same, it means at any time. Okay, rarely it can happen, means both are used to call at the same time, it should be occurred at rarely. So in the same way, the system may leads to deadlock only at rare conditions. So the avoidance ensures that a system will never enter an unsafe state. So we have to take care that, and we have to ensure that whatever the system we are using will never enter an unsafe state. So the main thing to avoid a deadlock is we have to make our system to unsafe state. To maintain your system in unsafe state, it never leads to deadlock. So that is a one method to avoid the deadlock. So this deadlock avoidance can be explained by using Banker's algorithm. Now let us see what is this Banker's algorithm. The example for this deadlock avoidance is deadlock avoidance by using Banker's algorithm. So here I am taking one example to explain Banker's algorithm directly. So before going to discuss about the Banker's algorithm, the points, the conditions you have to be take care while you're using, if you're dealing with the deadlock avoidance. There is a chance for multiple instance. One, each process must have prior claim maximum use, and when a process requests resources, it may have to wait. So you have to think, means whenever the process is requesting for resources, it may have to wait. And when a process gets all its resources, suppose P1 get all its resources, means up to 10 it has used all the resources, and P2 uses 5 resources, whatever it is allocated. So when a process gets all its resources, okay, it must return them in a finite amount of time. So whenever this work is over, it has to return that resources to another process. So so that the other process can use that resources. So these conditions we have to take care to deal with the deadlock avoidance. Let us take one example. So in this example, I have to check whether a system is in safe or unsafe. So if your system is in safe, and what is the sequence that it is following to determine if it is a safe state. Okay, so let me take the example. So here I am the process, I am taking process P0, P1, P2, P3, P4. Total 5 process I am taking, and the allocations for each process at starting, I am taking 3 resources A, B, C. This A, B, C is any type of resources. The P0 is using 3 resources A, B, C. So starting their allocations will be A is 0, means P0 allocation for A resources is 0, and B is 1, C is 0. So like that, P1 A allocation is 2, 0, 0, 3, 0, 2, 2, 1, 1, and 0, 0, 2. And here in the problem, I'm giving the total allocations for this, means the total that this process this resource A can hold, and this B resource can hold, and C resource can hold. So that I am giving is total is, let me write here, total A resource is 10, B is 5, and C is 7. So this is I am giving, this is the total resources for A can hold, and B can hold, and C can hold. So now here allocation is over. I allocated means at the starting A resources for P0 process it only 0, for P1 process it allocates 2, P2 process 3, like that. Now the maximum it can allocate, the P0 can allocate it 7, 5, 3, and P1 3, 2, 2, and P2 9, 0, 2, P3 4, 2, 2, and P4 5, 3, 3. So let us take this is the process, allocation, and the maximum. Now I have to find out the current work, that means the available. So each process allocation is given, and the maximum is we know, and the total resources, the allocation we know, but we want the current work, how much current work it has to handle. If you know the total and the allocation, starting allocation and the total, if you minus the allocation, present allocation from total, you will get the current work available, still work available. Okay, the A resources has to be multiplied with subtracted with the total allocation. So that we will do. And next is the remaining need. Remaining need means still how much need we need for P0 process, P1 process, P2 process, like that. So that can be calculated by using maximum minus allocation. So if you do minus from maximum minus allocation, you will get the remaining need. So this P0 can hold the maximum this. Okay, if you minus from maximum minus allocation, you will get the remaining need. Now let us calculate. First we will calculate the remaining need. So remaining need can be done maximum minus allocation. So we have to calculate from each resources. So this is A, B, C. So A minus A, B minus B, C minus C. So this, like this, you have to be subtract. Okay. So A minus B, 7 minus 0, you get 7. 5 minus 1, 4. 3 minus 0, 3. Now 3 minus 2, 1. 2 minus 0, 2. 2. 9 minus 3, 6. 0. 2 minus 2, 0. 4 minus 2, 2. 2 minus 1, 1. 2 minus 1, 1. 5 minus 0, 5. 3 minus 0, 3. And 3 minus 2, 1. So this is the remaining need we get. Now we have to calculate the current work. So what this P0 process current work was, means the current work, how we are going to calculate. So the current work is, first you have to know the maximum, the allocation for A. Up to now the A is allocated 2, 3, 5, 6, 7. The A resources allocated 7, and the B resources allocated 2, and the C resources allocated 5. 2 plus 2, 4 plus 1, 5. So total 7 to 5 was allocated. We are get the total. We know the total. So if you minus total minus allocation, you will get the current work. So the total is 10 for A and the allocation is 7. So 10 minus 7, we'll get 3. Okay, and for B, the 2 is allocated and the total it is 5. So if you do 5 minus 3, you will get the current work of B resources. In the same way, C is 7 and here the allocation is 5. 7 minus 5, excuse me, you will get 2. Sorry, 5 minus 2, you will get 3. 3, 3, 2. Okay, we get the current work now. So we have to calculate whatever the sequence, that is a safe process, we have to be arranged in a sequence. So in this P0, P1, P2, P3, P4, we have to find out which process is in safe state. So that process have to be assigned first. Next, we have to calculate the next safe state process so that the deadlock can be avoided. If you arrange all the process in a safe state to use the maximum the resources, whatever it is provided for that, by using the resources, by completing the work, which process will come in a safe state first, that we have to be calculated. That can be calculated by using an algorithm, that is a Banker's algorithm. The Banker's algorithm is having the formula like need I is less than or equal to work. If the need I, that is the need is this, okay, the remaining need is present here for P0 and for P1 and P2, P3, P4 like that. This is a remaining need. So the need is less than or equal to work, that is a current work. Then you have to calculate work is equal to, means you have to update that process, work plus allocation. So this work is equal to work plus allocation. Why we are doing this? Because the process release allocation. Whenever the condition, this condition is satisfied, we have to arrange that process in a sequence, and that work should be, that resources should be allocated to other process. Means we are just releasing that resources. Means suppose the P0 is using some current work. So if this work is over, we just adding these resources to another process so that that process may use that resources. So like that, whenever the work is over, we have to release the process. That is the main condition in the deadlock avoidance. So now we will calculate what is the P0. So first we'll calculate the P0. This P0 is in safe. If it is in safe, then we have to be arranged in sequence. This need is 743. P0 need is 743. 743 is less than or equal to, what is the current work? 332. Is less than or equal to 332. So we have to check each resources, not total. If 7 is less than or equal to 3, 4 is less than or equal to 3, 3 is less than or equal to, like that you have to check, not the total value. Okay, the total value should not be checked because each resources is separate. So the need of A resource, need of B resource, need of C resource, and the current work of A resource, current work of B, and current work of C. So this 743 is less than or equal to 332. No, this is not true. So the P0 is not in a safe state. So just go for next P1. Means that P0 resource is not sufficient to execute the complete the P0 work. Okay. Now we will go for P1. The P1 need is the P1 need is 1, 2, 2. So just 1, 2, 2 is less than or equal to work. That is the current work is 332. Yes, 1 is less than or equal to 3. 2 is less than or equal to 3. 2 is less than or equal to 2. Okay, this condition is satisfied. Whenever the condition is satisfied, we have to calculate the work. That is 332 plus, what is the allocation for this P1? The allocation for P1 is 200. So the allocation of P1 is 200. So that we have to be add. So the W work is equal to 332 plus 200 will get 532. So now update this with 532. Now the current work available is 532. Okay. So now arrange the in sequence. So P1 is enter into sequence because it completed its work. The process P1 is successfully executed. And next I'll go for P2. So the P2 need is 600. 600 is less than or equal to, what is the current work need now? That is 532. 532. Now check. 6 is less than or equal to 5. No. So the first condition itself is failed. So just discard. Then go for P3. Now check. What is the need of P3? P3 need is 211. Is 211 less than or equal to current work 532? Yes, 2 less than or equal to 5. First resource satisfied. 1 less than or equal to 3 satisfied. 1 less than or equal to 2 satisfied. Okay. Now calculate the work. The work is the current work. What is the current work now? 532 plus allocation. Allocation of P3 is 211. Add 211. So you get 743. A resources 7, B resources 4 and 3 resources 3. So now the current work is updated with 743. Okay, now enter P3. So the P3 process is also completed. So it entered into the safe state. So P1, next sequence is P3. Now calculate P4. So what is the need of P4? 531. So 531 is less than or equal to, what is the current work now? 743. 743. Now I had to check. 5 is less than or equal to 7, satisfied. 3 less than or equal to 4, satisfied. 1 less than or equal to 3, satisfied. So I had to calculate work is equal to, the current work is 743. And what is the allocation here? 743, P4 allocation 002. So just add 002. So you'll get 745. So now update the current work with 745. So P4 is also entered into the sequence because it is in safe state. Now again come to P0, because we are allocating the, whenever the process work is over, we are just releasing those resources to other process. So that's why it is in increasing order. The current work available is, the resources availability is increasing. So whenever it is increasing, so that the other process may execute, okay, without deadlock. So again the process P0 I have to check. Now check P0. P0. So current work is now 7, means the need of P0 is 743. Now I have to check the need. 743 is less than or equal to, what is the current work? 745. 745. Check. 7 is less than or equal to 7. Okay, satisfied. 4 is less than or equal to 4, satisfied. 3 less than or equal to 5, satisfied. So now calculate the work. Work is equal to, the current work is 745 and the allocation for P0. What is allocation for P0? 010. So that I have to be add. So total you will get 755. So update this 745 with 755 because P1 is also enter into, P0 is also entry into the sequence because P0 is completed his work. So whenever it is completed its work, it releases the resources. So that's why the 745 is updated with 755. Now P2, P1. So P1, P1 is already executed. So no need to, because it is also already entered into the sequence. It entered into the safe state. Now go for P2. Okay. Now calculate P2. What is the need of P2? P2 need is 600. So 600 is less than or equal to, what is the current need? 755. 7. The current available work is 755. Now check, is this condition is satisfied or not? 6 is less than or equal to 7. Okay. 0 is less than or equal to 5. 0 is less than or equal to 5. This condition is satisfied. So P2 is also entered into the safe sequence. Now W is equal to the current work 755 plus allocation. What is the P2 allocation? 302. So what is the P2 allocation, right? P2 allocation was, so P1, P0 is over, P1 is over and the P2 allocation was 302. 302. So now just add 751,057. So the allocation here is updated with 1057. Okay, so this is the current work available because all process or enter into the safe sequence by using the resource allocation. With the help of the current work available, the process are executed in this sequence. This is a safe sequence, safe state P1. If you execute the process, all these 5 processes in this sequence, the deadlock will not occur. So this is how we can find out the process that are executing in a system by using Banker's algorithm to avoid the deadlock. Thank you.